morning, good afternoon, good evening, whatever the case may be. We are back and better than ever for part 2 of Roots of Complex Numbers. Hopefully this will be pretty quick. Loving the Louie Louie by the Kingsmen. Let's get to it. When we left off, we had found the fourth roots of -4, and we put them in the form a plus bi. So we had 1 plus I, 1 minus I, -1 plus I, -1 minus I. And we're going to use that info to write z to the fourth plus 4, which, right here, as a product of real quadratic factors. And I think you can probably think about this and maybe do it in your head. But again, we had the roots 1 plus or minus I, and we had the roots 1, -1 plus or minus I. Okay, so let's think about this in terms of quadratics. Let's see. 1 plus or minus I, here, they have the sum, if I added them together, that's what sum is, of 2, right? And their product, the product of 1 plus or minus I, would be 2 as well. Say yes? Yes. So that means that they must come from the quadratic factor z squared minus 2z plus 2, which reminds me, 2z or not 2z, sorry, okay. And then -1 plus or minus I, they have a sum of -2, and they have a product of 2, which means that they must come from the quadratic factor z squared plus 2z, or not 2z, plus 2. That's the question, I believe. And so, z to the fourth plus 4 must be equal to the product of those two quadratics. Isn't that awesome? Love it. And I'm taking my time writing it out. So there we go. Done, done, done. One more thing to discuss with complex numbers, and that is the nth roots of unity. Read this carefully. The nth roots, it seems complicated, but it's really not. The nth roots of unity are the solutions of z to the n equal to 1. Unity 1, right? So whatever power that you have there, like the z to the fifth, would be the fifth roots of unity, because they are equal to unitas, uno, unce. Unce isn't a word, but whatever, 1. So find the 3 cube roots of unity and display them on an Argand diagram. If w is the root with smallest positive argument, show that the roots are 1, w, and w squared, and that 1 plus w squared equals 0. Easy peasy. So these would satisfy z cubed equal to 1. So we've been through this before. We know that 1 is actually 1 plus 0i. So that means that 1 is equal to cis 0. Think about that, right? Because the cosine of 0 is 1. Think about your Argand diagram. And that is equivalent to cis of 0 plus k2 pi, or 2k pi. And of course, k is an element of the integers. Never can be too careful. So now we have z cubed is equal to cis k2 pi. Here we go. You see where we're going. So that means z, using de Moivre, I'll write it again here, r cis theta to the n. We're just going to this form because we're in this form now. Actually, we're not. Now we're going to be cis of k2 pi to the 1/3 power. Now we're in this form. And of course, 1 to the 1/3 is 1, and then we're going to multiply this cowboy by 1/3, and we get z is equal to cis k2 pi over 3. Awesome, awesome, awesome. Thank you, Demois. And so if we let k equal to 0, 1, and 2, then we get z equal to, and we're doing that because we're only looking for 3 roots, correct? Z equals cis 0, cis 2 pi over 3, cis 2 pi over 3, and of course cis 4 pi over 3. We're getting there, we're getting there. So that means for here, z is equal to 1. For cis 2 pi over 3, that would be cosine 2 pi over 3, negative 1/2 sine 2 pi over 3, root 3 over 2. So that would be negative 1/2 plus root 3 over 2i. And then for 4 pi over 3, they're both negative, so that would be negative 1/2 minus root 3 over 2i. Okay? So, here we go. If w is the root with the smallest positive argument. Oh, we have to display it on an Argonne diagram. Okay, so here we go. Sorry about that. So I'm going to just do R for real, I for imaginary, and we'll go pink for these guys. So for 1, we'd go here, right? There's 1. And then for, let's see, negative 1/2 root 3 over 2, that's going to be at the 2 pi over 3 dealio, and then this is going to be at the 4 pi over 3, negative 1/2 negative root 3 over 2. And remember one of those properties, if these are the roots of unity, then they're all going to lie on the same circle, especially if you're drawing the circle. Oh! And again, from here to here is the same as from here to here. They cut off the same arcs, and the distance from this point here to this point here is the same as from this point here to this point here, and from this point here to this point here. So we would have a regular triangle or an equilateral triangle there. All right. So again, I mentioned this occurs at 2 pi over 3, right? That's the argument. Right here, 2 pi over 3, because this is the point, negative 1/2 root 3 over 2. Clearly, 2 pi over 3. So that is the smallest positive argument. So don't give me any zero nonsense. It's the smallest positive argument. Okay, so show that the roots are 1, w, and w squared. Okay. Well, so w equals cis 2 pi over 3, yes. Okay, and then w squared is equal to cis 2 pi over 3 squared, yes, which is equal to, by de Moivre, 1 squared is 1, and then we go through and multiply this by 2, so that would be cis of 4 pi over 3. It's a lot of stories, baby. Just say, yes, of course, right? So clearly the roots are 1, w, and w squared, where w equals cis of 2 pi over 3. Okay? And 1 plus w plus w squared is equal to 1 plus, what's w? Cis 2 pi over 3, right? And we found cis 2 pi over 3 to be negative 1/2 plus root 3 over 2i, yes? And plus w squared, which is cis 4 pi over 3, which is negative 1/2 minus root 3 over 2i. Okay, so kabam, kabam, right? And then a negative 1/2 and a negative 1/2 and a positive 1, those all cancel out, so that is equal to 0 as required. So there we go, a little bit longer than I thought, sorry about that. Hope you enjoyed it. I certainly did. And let's cap it off the right way, shall we? Let's give it to him. I am... Oh!